Welcome! In this session, we'll tackle an exciting problem from LeetCode, number 2049, titled Count Nodes with the Highest Score. We'll explore its nuances, break down the solution approaches, and help you master the problem step by step. Let's dive in. In this problem, you are given a tree with n nodes labeled from 0 to n1, where the root node is always 0. This tree is described using a parents array of size n. In this array, parents, I, tells us the parent of node I. For the root node, parents, 0, is -1 because it has no parent. Now, the task involves removing a node from this tree, which splits it into several subtrees. The score of a node is calculated as the product of the sizes of all these subtrees that are formed after its removal. Specifically, when you remove a node I, the resulting subtrees include those rooted at its children and the remaining part of the tree, which excludes the subtree containing I. Your goal is to determine how many nodes achieve the highest score across all nodes in the tree. To better understand the problem, let's walk through an example. Suppose the parents array is given as -1, 0, 0, 1, 1, 2, 2. This represents a tree with 7 nodes. The tree structure looks like this. Node 0 is the root, and it has 2 children, nodes 1 and 2. Node 1 has children 3 and 4, while node 2 has children 5 and 6. This forms a balanced binary tree with the root at 0. The task is to calculate the score for each node when it is removed and then find out how many nodes have the highest score. Now, let's compute the scores for each node. Starting with node 0, removing it splits the tree into 2 subtrees rooted at 1 and 2. Since both these subtrees have 3 nodes each, the score of node 0 is 3*3 equals 9. For node 1, removing it creates subtrees rooted at 3, 4, and the part of the tree containing 2. The sizes of these components are 1, 1, and 4, respectively, so the score is 1*1*4 equals 4. Similarly, for node 2, removing it creates subtrees rooted at 5, 6, and the part of the tree containing 1. The score is again 1*1*4 equals 4. For node 3, removing it results in subtrees rooted at 4, the part of the tree containing 1, and the part of the tree containing 2. The sizes are 1, 5, and 3, giving a score of 1*5*3 equals 15. The same calculation applies to nodes 4, 5, and 6, each of which also has a score of 15. The highest score is 15, and there are 2 nodes, 3 and 4, that achieve this score. Therefore, the output is 2. Let's consider another example where parents equals -1, 2, 0, 2, 0. Here, the tree has 5 nodes. The structure is as follows. Node 0 is the root, and it has 2 children, nodes 2 and 4. Node 2 has 2 children, nodes 1 and 3. This forms a tree with a root, 1 intermediate node, and 2 levels of children. Just as before, we calculate the score for each node when it is removed and identify how many nodes achieve the highest score. Continuing with the example, for node 0, removing it splits the tree into subtrees rooted at 2 and 4. The sizes are 3 and 1, so the score is 3*1 equals 3. For node 1, removing it results in subtrees rooted at 3, 2, and 4. These have sizes 1, 4, and 1, respectively, giving a score of 1*4*1 equals 4. For node 2, removing it creates subtrees rooted at 1, 3, and 4, with sizes 1, 1, and 4, resulting in a score of 1*1*4 equals 4. Similarly, for nodes 3 and 4, the scores are also 4. Since the highest score is 4, and nodes 1, 2, and 3 achieve this score, the output is 3. To ensure our solution handles all scenarios, we should consider a few edge cases. For instance, in the case of the smallest tree where n equals 2, removing the root splits the tree into a single subtree, while removing the child leaves the root as the entire tree. For very large trees with up to 10⁵5 nodes, it's important to calculate subtree sizes and scores efficiently. Additionally, we must handle unbalanced trees, such as those that form a single path, as well as perfectly symmetrical trees, where multiple nodes may share the same score due to symmetry. These considerations help ensure the solution is robust and handles all valid tree structures effectively. To tackle this problem, let's first consider the brute force approach. The intuition here is straightforward, since the goal is to calculate scores for each node based on the sizes of its subtrees and the remaining nodes. We can iterate through all the nodes one by one. For each node, we remove it, calculate the sizes of its subtrees and the complement tree, which consists of the remaining nodes, and compute the product of these sizes. The implementation involves traversing the tree repeatedly to calculate subtree sizes for every node. After computing the product for each node, we track the maximum score and count the nodes that achieve this score. However, this method is computationally expensive. Calculating the sizes of subtrees requires a full traversal of the tree, and doing this for every node results in an overall time complexity of n squared. This quadratic complexity makes the brute force approach impractical for larger trees, especially given the problem constraints that allow up to 10,000 nodes. The repeated and redundant calculations lead to excessive overhead, making it clear that we need a more efficient solution. A more efficient approach involves using post-order traversal with depth-first search, DFS. The intuition here is to calculate subtree sizes for all nodes in a single traversal, rather than recalculating them repeatedly. Post-order traversal is particularly well suited for this because it processes child nodes before their parent, which aligns perfectly with the need to calculate subtree sizes recursively. For any given node, its score is the product of the sizes of its left subtree, right subtree, and the complement tree. The complement tree size can be easily determined as the total number of nodes minus the size of the subtree rooted at the current node. To implement this, we first build an adjacency list representation of the tree from the given parents array. Then, using DFS, we compute subtree sizes and scores for each node in one pass. During this traversal, we also keep track of the maximum score and count how many nodes achieve it. This approach has a time complexity of n, as it involves a single traversal of the tree, and its space complexity is also n, which makes it both time efficient and memory efficient. While a breadth-first search, BFS, approach could also compute subtree sizes iteratively, it introduces additional complexity in managing the order of processing nodes and resolving parent-child dependencies. Therefore, DFS is a more natural and straightforward choice for this problem. The strategy we've chosen is the post-order DFS approach, and there are several reasons why it stands out. First, DFS naturally aligns with the hierarchical structure of trees, allowing us to process child nodes before their parent. This makes it particularly well suited for calculating subtree sizes and scores in a single traversal. Its recursive nature simplifies the logic for both traversal and computation. While the brute force method is conceptually simple, its inefficiency makes it unsuitable for larger inputs. On the other hand, DFS is viable but more complex to implement due to the added challenges of managing parent-child relationships in an iterative framework. Post-order DFS strikes an ideal balance, as it's both efficient, with n, time and space complexity, and straightforward to implement. This approach eliminates redundant calculations, ensuring optimal performance even for the upper constraint of 10,000 nodes. In summary, the post-order DFS approach is the most practical solution, offering simplicity, scalability, and efficiency, making it the clear choice for solving this problem effectively. To solve this problem, we need to work with a tree structure where each node is removed one by one. For every removal, we calculate a score based on the product of the sizes of the resulting subtrees, and our goal is to find the maximum score and count the nodes that achieve it. The first step in our algorithm is to parse the input and represent the tree using an adjacency list. This is a compact and efficient way to store the tree, allowing constant time access to any node's neighbors. For example, if we have a tree with node 1 connected to nodes 2 and 3, and node 2 further connected to nodes 4 and 5, the adjacency list for this structure would look like this: graph equals 1, 2, 3, 2, 1, 4, 5, 3, 1, 4, 2, 5, 2. Next, we need to calculate the size of the subtree rooted at each node, which we can achieve using a depth-first search, or DFS. By starting the DFS from any node, node 1, for instance, we recursively determine the sizes of all child subtrees and sum them up to get the total size for the current node. This lays the groundwork for efficient score calculations later in the algorithm. With the adjacency list in place, we can now calculate the subtree sizes using DFS in detail. For any given node, we initialize its size to 1, representing itself. Then, for each of its neighbors, if the neighbor is not its parent in the DFS traversal, we recursively calculate the subtree size for that neighbor. The size of the current node subtree is incremented by the sizes of all its child subtrees. Here's the code to achieve this. Def calculate underscore subtree underscore sizes, node, parent size equals 1, for neighbor in graph, node, if neighbor equals parent, size plus equals calculate underscore subtree underscore sizes, neighbor, node, subtree underscore sizes, node, equals size, return size. This function ensures that the subtree sizes are computed and cached in a dictionary or array for quick lookup during subsequent calculations. Once we have these subtree sizes, we move on to iterating over each node to calculate scores. Conceptually, we remove a node by excluding it from the DFS traversal. This divides the tree into multiple connected components, or subtrees. For each of these subtrees, we use the pre-computed sizes to calculate the product of their sizes. Additionally, we consider the size of the complement tree, which is the total number of nodes minus the size of the current subtree, to include all components in the score calculation. After calculating the product of subtree sizes for a given node, we compare this score to the current maximum score. If the score is higher, we update the maximum score and reset the count to 1, indicating that only this node achieves the new maximum. If the score equals the maximum score, we simply increment the count. To ensure the algorithm continues smoothly, we conceptually restore the removed node after processing. For tracking results effectively, we use two variables, max underscore score to store the highest score encountered so far, and count to keep track of how many nodes achieve this maximum. Finally, once all nodes have been processed, we return both the maximum score and the count. This systematic approach ensures that we efficiently compute the required results while minimizing redundant calculations. The algorithm relies on key insights, such as using DFS to pre-compute subtree sizes, which drastically reduces computational overhead. By storing subtree sizes, we avoid recomputing them for each node, further improving efficiency. It's also important to handle edge cases, such as trees with a single node, highly unbalanced trees like chains, or large trees with dense structures, ensuring that the algorithm performs consistently across different inputs. To summarize, the core data structures in this algorithm include the adjacency list for representing the graph, a dictionary or array to cache subtree sizes, and two variables, max underscore score and count, for tracking the outputs. The adjacency list is a memory-efficient way to store the tree structure, while the subtree size cache allows quick access to pre-computed values during score calculation. In terms of complexity, the algorithm is highly efficient. Calculating subtree sizes using DFS takes n time, as each node is visited once. Iterating over the nodes to calculate scores also takes n, resulting in an overall time complexity of n. For space complexity, the adjacency list and subtree size cache require n space, making this approach scalable for large trees. These optimizations ensure that the algorithm runs efficiently, even for edge cases like single-node trees, unbalanced chains, or dense structures, while maintaining clarity and simplicity in implementation. Here, we begin by importing the defaultIct class from the collections module to help us efficiently represent the tree structure. Next, we define the countHighestScoreNodes method within the solution class, which takes a list called parents as input. This list represents the tree, where parents, I, indicates the parent of node I, and a value of -1 means the node is the root. We calculate n as the total number of nodes and initialize tree as a defaultIct of lists to store the adjacency list representation of the tree. Then, we loop through each node in the parents list using enumerate. For non-root nodes, we append the node to its parents list in the tree, effectively building the adjacency list. Next, we define a helper function, calculate underscore subtree underscore sizes, which uses a post-order depth-first search (DFS) approach to calculate the size of each node's subtree. The function starts with a size of 1 to include the current node itself. For each child of the current node, it recursively calls the function, adding the return size to the current node's total size. This value is then stored in the subtree underscore sizes list for the respective node. Finally, the function returns the total size of the subtree rooted at the current node. We invoke this function starting from the root node, which we assume to have an index of 0. At this point, the subtree underscore sizes list is fully populated with the sizes of all subtrees. We also initialize max underscore score and count to 0, which will help us track the highest score encountered so far and how many nodes achieve it. Now, we calculate the score for each node. We iterate over all the nodes in the tree using a for loop. For each node, we initialize score to 1, as we'll multiply values to it, and total underscore size to n, which represents the total number of nodes. We then multiply score by the size of each of the node subtrees, accessed via subtree underscore sizes, and decrement total underscore size by the size of each subtree. This ensures that total underscore size eventually represents the size of the remaining tree when excluding the current node and its subtrees. If the remaining tree has more than one node, we multiply score by its size, adjusted by subtracting 1 to exclude the current node itself. Once the score for the node is calculated, we compare it with the current max underscore score. If the new score is greater, we update max underscore score and reset count to 1, as we found a new highest score. If the score matches max underscore score, we simply increment count since another node achieves the same maximum score. Finally, after completing the loop for all nodes, we return count, which represents the number of nodes with the highest score. Here, we start by defining the solution class and the method countHighestScoreNodes. The goal of this method is to calculate the number of nodes that yield the highest score when the tree is divided into subtrees. First, we take the parents array, which represents the parent-child relationships in the tree, and build an adjacency list using a hash map. Each parent node is mapped to a list of its child nodes, ensuring we can easily traverse the tree later. Next, we initialize an array subtree sizes to store the sizes of the subtrees for each node. To compute these sizes, a helper method calculate subtree sizes is called, performing a post-ordered depth-first search starting from the root node, which is assumed to be node 0. Once the subtree sizes are calculated, we prepare to iterate through each node to compute its score. We initialize max score to track the highest score encountered and count to count how many nodes achieve that score. The process for calculating scores begins by iterating through each node and initializing its score to 1. Additionally, a variable total size is set to the total number of nodes, representing the size of the entire tree. Now, for each node, we check if it has child nodes by verifying its presence in the adjacency list. If the node has children, we iterate through each child node. For each child, we multiply the current score by the size of the subtree rooted at that child, essentially considering the contribution of that subtree to the score. Simultaneously, we subtract the size of that subtree from total size to account for the portion of the tree that has already been processed. After accounting for all subtrees, we also consider the remaining part of the tree that excludes the current node and its direct subtrees. If this remaining part has more than one node, its size is included in the score calculation by multiplying it with the current score. Once the score for the current node is computed, we compare it to the max score. If the current score exceeds the max score, we update max score and reset count to 1, as this is now the highest score. If the score matches the max score, we simply increment the count, reflecting another node with the same maximum score. Finally, after iterating through all nodes, the method returns the count of nodes that achieve the highest score. The helper method calculate subtree sizes is crucial for determining the size of the subtree rooted at each node. This method performs a depth-first search, starting from the given node and recursively traversing its children. For each child, it adds the size of the subtree rooted at that child to the current node's size. This ensures that the size of the current node's subtree includes not only the node itself but also all its descendants. Once the size for a node is fully calculated, it is stored in the subtree sizes array, making it accessible for the score calculation in the main method. The method then returns the calculated size, which gets propagated up the recursion stack to contribute to the size computation of its parent nodes. This post-order traversal ensures that we compute subtree sizes bottom-up, enabling us to build accurate results for the entire tree structure. To solve this problem, we start by constructing the tree from the parents array using an adjacency list representation. Here, the root node is 0 because it has a parent of -1. Node 0 has two children, nodes 1 and 2. Then, node 1 has children 3 and 4, and node 2 has children 5 and 6. This gives us a clear hierarchical tree structure where node 0 is the root, and we can see all its descendants. This structure will help us in the next step, where we calculate the size of each subtree. Now, using a post-order depth-first search, we determine the size of each subtree starting from the leaf nodes and working our way back up to the root. Leaf nodes like 3, 4, 5, and 6 each have a size of 1 because they have no children. For node 1, which has children 3 and 4, its subtree size is 3, calculated as 1 plus 1 plus itself. Similarly, node 2 has a subtree size of 3, including nodes 5 and 6. Finally, the root node 0 has a subtree size of 7, which is the total number of nodes in the tree. These subtree sizes are crucial for calculating scores in the next step. Using the subtree sizes, we now calculate the score for each node based on the product of the sizes of its subtrees and the size of the remaining part of the tree. For the root node 0, its subtrees are of size 3 and 3, but there is no remaining part of the tree, so its score is 3 times 3 times 0, which equals 9. For nodes 1 and 2, each has subtrees of size 1 and 1, with a remaining tree size of 4, giving them scores of 4. Leaf nodes like 3, 4, 5, and 6 have no subtrees, but their remaining tree size is 6, so their scores are 6. The highest score is 9, achieved only by node 0. Therefore, the output for this example is 1, indicating one node with the highest score. In this second example, we have a simpler tree structure with root node 0, which has two children, nodes 1 and 2. Using postorder DFS, we find that nodes 1 and 2, being leaf nodes, each have a subtree size of 1. The root node 0 has a subtree size of 3, which includes itself and its two children. With these subtree sizes, we calculate the scores. For node 0, the subtrees are of size 1 and 1, but there is no remaining part of the tree, so its score is 1 times 1 times 0, which equals 1. For nodes 1 and 2, they have no subtrees, but the remaining tree size is 2, so their scores are 2. The highest score is 2, achieved by both nodes 1 and 2. Thus, the output is 2, indicating two nodes with the highest score. In the final example, the tree structure is a straight line. Node 0 is the root and has one child, node 1, which in turn has one child, node 2. Calculating subtree sizes, node 2, being a leaf, has a size of 1. Node 1 has a size of 2, which includes itself and node 2. The root node 0, which includes all nodes, has a size of 3. Now, for scores, node 0 has a single subtree of size 2, with no remaining tree, so its score is 2 times 0, which equals 2. Node 1 has a single subtree of size 1, with a remaining tree size of 1, giving it a score of 1. Finally, node 2 has no subtrees, but the remaining tree size is 2, giving it a score of 2. The highest score is 2, achieved by nodes 0 and 2. Therefore, the output is 2, indicating two nodes with the highest score. To analyze the time complexity of our solution, we need to consider the major steps involved. First, we have the tree construction, where we build an adjacency list from the parents array. Since this array has a size of n, and we process each element once, the time complexity for this step is O(n). Next, we perform a postorder depth-first search, or DFS, to calculate subtree sizes. In this traversal, each of the n nodes is visited exactly once, and the work done per node is constant, giving us another O(n) time complexity. Lastly, we calculate the score for each node. Here, we iterate over all n nodes, and for each node, we loop through its children. Across all nodes, the total number of children is n1, which is the number of edges in the tree. So, the inner loop contributes O(n) in total, and since computing the product of subtree sizes and the remaining tree size takes constant time per node, the overall complexity for this step is also O(n). Now, when we sum up the contributions from all these steps, the total time complexity becomes O(n) for tree construction, plus O(n) for the DFS, plus O(n) for the score calculations. This simplifies to an overall time complexity of O(n). For the space complexity, we start with the adjacency list representing the tree. The tree dictionary contains an entry for each node, and since each node stores a list of its children, the total space required is proportional to the number of nodes and edges, which is O(n). Then, we have the subtree underscore sizes array, which uses O(n) space as it stores one value per node. Lastly, the recursive DFS function uses stack space proportional to the height of the tree. In the worst case of a skewed tree, the height is O(n), while in the best case of a balanced tree, the height is O log n. Therefore, the call stack requires O(n) space in the worst case. Adding everything together, the total space complexity is O(n) for the adjacency list, plus O(n) for the subtree sizes array, plus O(n) for the DFS call stack in the worst case. This results in an overall space complexity of O(n). Looking at different scenarios, in the best case where the tree is perfectly balanced, the DFS call stack depth is O log n. However, since all nodes still need to be processed, the time complexity remains O, n, and the total space complexity is still O, n, when accounting for the adjacency list and subtree sizes. For an average case, which is a typical tree structure, the time complexity remains O, n, and the space complexity also remains O, n. In the worst case, with a highly skewed tree, the DFS call stack depth reaches O, n, so the space complexity is O, n, while the time complexity remains O, n, as all nodes are still visited. When comparing this optimized solution to a brute force approach, the difference is significant. A brute force method would compute the score for each node by explicitly iterating over all possible subtrees. Calculating subtree sizes and scores independently for each node would require traversing the entire tree for every node, leading to a time complexity of O, n squared. In contrast, our optimized solution avoids redundant calculations by pre-computing subtree sizes with a single DFS traversal, which reduces the time complexity to O, n. Mathematically, the post-order DFS ensures that each node is visited exactly once, contributing O, 1 work per node. With n nodes, this results in O, n time complexity. For space, the adjacency list and subtree sizes array each require O, n, and the DFS call stack depth is at most O, n. Thus, the total space complexity is O, n. This makes the optimized solution highly efficient, even for large input sizes, adhering to the problem's constraints. When working with this problem, there are a few common mistakes that can trip you up. First, misunderstanding the tree structure is a frequent issue. A tree is connected and acyclic, meaning there are no cycles and each node has a unique connection. Treating it like a general graph with cycles, or overlooking these unique connections, can lead to invalid solutions. To avoid this, always verify that the input adheres to tree properties, and remember to test edge cases like single-node trees or very small trees. Another common mistake is inefficiently recalculating subtree sizes. If you recompute the subtree sizes from scratch for every node removal, it will lead to redundant calculations and poor performance. Instead, you can use dynamic programming or a depth-first traversal to pre-compute and store subtree sizes for reuse. Finally, overlooking edge cases can cause problems. For instance, a tree with just one node, a perfect binary tree where all nodes are at the same depth, or a highly imbalanced tree where nodes form a straight line. These scenarios need special attention to ensure your solution is robust and error-free. Another potential pitfall involves overflow in score calculations. When dealing with large trees, the product of subtree sizes and other factors can become so large that it exceeds the limits of standard integer types in some programming languages. To address this, you can use modular arithmetic to keep numbers manageable, or switch to data types that support larger values. Additionally, incorrect handling of the complement subtree can lead to errors. After removing a node, the remaining part of the tree, the complement, is crucial for calculating the score. If its size is overlooked or calculated incorrectly, the results will be inaccurate. To handle this correctly, calculate the complement as the total number of nodes minus the sizes of all subtrees rooted at the remaining nodes. This ensures that your calculations for the complement are both accurate and efficient. To perform well in interviews, understanding tree-specific optimizations is key. Problems involving trees can often be solved more efficiently using depth-first search or breadth-first search. Recognizing when to use these traversal techniques helps reduce time complexity significantly. Another powerful strategy is dynamic programming on trees. By storing intermediate results, such as subtree sizes or scores, you can avoid redundant computations and make your solution more efficient. Breaking down the problem is also vital for tackling complex tree scenarios. Dividing the tree into smaller subtrees often simplifies calculations, making the problem more manageable. Lastly, in the interview setting, clear communication of your thought process is critical. Make sure to articulate how you plan to handle edge cases, optimize calculations, and avoid unnecessary operations. This not only demonstrates your problem-solving skills but also reassures the interviewer of your understanding of the problem. Practicing related problems can deepen your understanding of tree-based algorithms. For example, problem 310, minimum height trees, asks you to find the root nodes that minimize a tree's height, testing your knowledge of tree properties and traversal techniques. Problem 124, binary tree maximum path sum, focuses on calculating the maximum path sum in a binary tree, which is similar in terms of optimizing calculations related to subtrees. Problem 236, lowest common ancestor of a binary tree, challenges you to efficiently find relationships between nodes, making it another excellent exercise for working with tree structures. Finally, problem 1339, maximum product of split binary tree, is closely related to this problem, as it also involves splitting a tree and calculating products of subtree values. Practicing these problems will not only reinforce your tree traversal skills but also give you insights into different variations of tree-based challenges. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach involves removing each node, manually calculating subtree sizes and scores. While simple to implement, it's computationally expensive, often with a time complexity of n squared or worse. A more efficient method is using DFS with memoization. By traversing the tree with depth-first search and caching intermediate results like subtree sizes, you can significantly optimize the time complexity to n, though it does require additional memory. Post-order traversal is another effective option. By processing the tree in a bottom-up manner, you can calculate subtree properties efficiently and avoid redundant computations. However, you'll need to handle the complement subtree carefully. Finally, iterative DFS is an alternative to recursive DFS, using an explicit stack to avoid stack overflow in very deep trees. While this method is suitable for constrained environments, it can be less intuitive to implement compared to recursive approaches. Each method has its strengths, so the choice depends on the specific constraints and requirements of the problem. Great job! We've summarized the problem, highlighted key concepts, and discussed important takeaways. Remember, consistent practice is the key to mastering data structures and algorithms. Thanks for joining, and don't forget to like, share, and subscribe for more insights. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!